Hello everyone, myself Sai Prasad, Alexa in Akhlabad High School and the Junior College. Welcome to a series of the lectures of first year chemistry. We have started our discussion of periodic classification of elements in our previous sessions. We have discussed the basic periodic tables, the different models of periodic tables. Then we have discussed the variation of different periodic properties in the periodic table. Right? We discussed what is an atomic size. Then we discussed about this ionization potential. How do atomic size vary in a group and period? Atomic size, first of all, what is an atomic size? Atomic size is the property that defines the distance between the center of the nucleus and the outermost orbital. How do that vary in a period? That is, it decreases from left to right in a period and increases from top to bottom in a period. Fine. And not only that, when it comes to ionization potential, it is defined as the minimum energy required to remove an electron from the outermost orbital. And we also know that the second IP is greater than the first IP. And when it comes to the periodic properties, it is exactly quite opposite to our atomic size ka behavior. What is atomic size behavior in period? It actually decreases, whereas the ionization energy it increases, right? And in the group it decreases. Okay. Based on that, we discussed 2 to 3 properties, that is, we discussed 2 properties on which the IP depends. The first one was atomic size and the second one was nuclear charge. On the same lines, let us have a discussion of few more factors which are influencing the IP, that is the screening effect. Screening effect or shielding effect. What do this mean? See here, when it comes to a normal atom, let us assume an atom is in spherical in shape, which means the electrons will be revolving in a circular orbit. Is it okay? For example, if my electron is rotating here, then one more electrons rotate here. It rotates here, which means whenever this electron is rotating in this path, in some case, at some instance, this electron will come to this path, or else this electron might come to this path, which means they may lie on the straight line. Okay, all 3 may not lie, but at least 1 or 2 electrons may lie on the same line, which means the nuclear charge effect will be very less on the outermost orbital when compared to these 2 electrons. Is it right? What is the reason? Because the electrons in between or in the initial orbitals are acting like a shield or a screen to the lastmost orbital. Is it clear? Did you understand what is shielding effect? Right? Once again, let me tell, the electrons in the innermost orbitals are acting like a shield to the electrons in the outermost orbital, which in turn reduces the effect of nuclear charge on the outermost orbital. Is it right? As the nuclear charge effect is reduced, therefore, we can remove this electron very easily, right? Yes or no? Which means shielding effect must be very high, then only IP can be low. Is it clear? Fine. The shielding effect can also be called as shielding effect, screening effect. That is, as screening effect is very low, IP will be very high. Is it clear? If there is no screening effect, let us assume 3 electrons are in different places, 1, 2 and 3. Okay, then there is no need of a screening, or else the normal IP will be continued. If not, if the electrons are in the straight line, or else this electron is being hidden by other 2 electrons, which means these electrons are acting like a shield. Clear? Did you understand? That is what I can relate it here. As as screening effect decreases, IP increases. As screening effect increases, obviously IP decreases. Clear? Did you understand? Fine. Now see here, what is the next property here? The extent of penetration of orbitals of valence electrons. Extent of penetration. What do you mean by the term penetration? Penetration is, if the nuclear charge increases, this electron has to move into inside orbital, right? These orbitals has to be, the outermost orbitals can be penetrated into inner side orbitals, right? That is, this can be varied with respect to the shape of an orbital. For example, if S has a highest, the better performant shape, better shape it has, because it is spherical in shape, whereas P is dumbbell, D is double dumbbell, like that, right? Whereas if the shape is very clear, then it is easy to penetrate through the orbitals. That is, the penetration of an orbital depends upon the shape of an orbital. That's why penetration is very high for s orbital when compared to p, when compared to d, and when compared to f. This is the order of penetration, right? If my valence electron is s orbital, then what do that mean? That is, IP should be high when compared to these three. Okay. The next one more factor is half filled and completely filled subshells. We already discussed a noble gas, that is, it is completely filled. Therefore, we got to know that those are highly stable elements, right? And not only that, there are few more examples such as sodium, let us assume. Not sodium, okay, let us assume nitrogen. Okay, nitrogen, its atomic number is 7. In order to be stable, it gains 3 more electrons to become stable, right? Which means it achieved neon configuration. Yes or no? That's what we learned from our 9th class, right? Which means n minus 3 will have more stability. Therefore, if there is more stability, the IP required to remove an electron will be very high. Is it clear? The stable atoms require more IP, right? In order to explain that, this is one more typical thing, and this is very important discussion about IP. That is, let us assume the second period elements, that is sodium, magnesium, aluminum, and the next silicon, phosphorus, and sulfur, right? If you observe here, Na has its configuration of 1s2, 2s2, 2p6, 3s1, whereas Mg has 3s2, whereas Al have again 3p. Yes or no? Which means if you observe, I know that in conventional it has to increases from left to right, right? See here, Na has some ionization potential I1, Mg has some ionization potential I2. Obviously, according to our conventional theory, this I2 will be greater than I1 because it has to increase from left to right, right? And when it comes to Al, it will be I3, right? Will it increase or decrease? Why I am telling? Because when it comes to Mg, Mg has an outermost configuration as 1s2, right? 1s2 is more stable than half filled. Whereas when it comes to Al, it has the outermost configuration as 2p1. Yes or no? Which means as long as we are moving, there are few elements which has more IP when compared to the next element. This is one of a typical example. Did you understand? This is how there are a few variations in group and period. Clear? Shall we move on to the next property? What all properties we discussed? The first one is metallic character, then atomic radius, then ionization potential. Let us move on to the next topic, that is electron affinity. The next property here is electron affinity. What is electron affinity? What is IP first of all? The energy required to remove an electron, right? Then the sodium atom or else a metallic atom will become as a unipositive ion, right? What if a chlorine atom, that is a non-metal, how many electrons does it have? It has 17 electrons. It requires one more electron to become 18, that is argon configuration. Isn't it? Yes or no? Chlorine requires one more electron, right? How did we learn in the sodium ka thing? When sodium is given some energy, that energy removes a electron from sodium, making it as Na plus. Isn't it? Whereas when it comes to chlorine, chlorine requires an electron, which means here we are giving an energy to the electron so that it comes out of the nuclear charge. Here the energy is released, right? Chlorine, it releases some energy, right? it releases some energy, that is nothing but electron affinity when an electron is added. Is it right? Did you understand? When we try to add an electron to the chlorine, this energy has to be removed, which means energy of electron has to be reduced in order to settle in the outermost orbital of an atom, right? Or else finally we can define electron affinity as the energy released when an electron is added to an outermost orbital of an atom to make a negative ion, right? When chlorine is added to when an electron is added to a chlorine, it becomes Cl minus and it releases some energy, that is nothing but electron affinity, or simply it can be called as electron gain enthalpy, right? It doesn't mean electron affinity and IP will be same, but in most of the cases both will differ with a little kind of number in magnitude, that is whether it is positive or negative, it differs, but most of the time their energy will be equated, right? That is what electron affinity. Yes or no? Now tell me, as IP increases, electron affinity has to decrease, right? Now see here, in a group IP decreases from top to bottom, obviously it will increase, isn't it? IP is energy required to remove an electron. Here EA is energy released when we add a electron, right? Whereas in a period IP increases, here it decreases. Yes, what could be the reason? Again you can write the same reason of nuclear charge or else atomic radius. Okay. Next, electronegativity. You have heard about electronegativity and electropositivity, right? Electronegativity is tendency to attract the pair of shared electrons towards itself, right? We all know that Na and Cl, right, they are sharing a single pair, right? Na has an extra electron, Cl has one electron less, which means this electron of Na and one last outermost electron of Cl, these both are pairing together to form a pair, right? That is bond pair. This electron, or else we can take some other example such as O2, the outermost orbital of O and O, this both electron combine together to form a pair. Towards which element this pair has to move? For example, O and O, it will be in between. For example, if it is H2O, right, towards which side this electron should concentrate more, either or towards H or towards O. That is, that property of an atom is called as electronegativity. Clear? Electronegativity is a property of an element which has tendency to attract the pair of bonded electrons, right, towards itself. Is it clear? Fine. How does that vary? It varies in such a way that it decreases from top to bottom in a group and increases from left to right in a period, right? Similarly, electropositivity is again opposite to it. Clear? Fine. What all properties we learned? We learned about atomic radius, ionization potential, electron affinity and electronegativity. And one more thing is metallic nature. If we tabulate that, this is one of the most important table. Based on this, you can attempt one long answer question also. See here, atomic radius increases in a group, obviously from top to bottom. It decreases in a period. And in conventional, IP decreases from top to bottom in a group and increases from left to right in a period. Okay, where does the discussion come? It comes in either 3A or 4A kind of elements only. We will have some kind of disturbance, right? Fine. When it comes to EA, it increases from top to bottom in a group and decreases from left to right in a period. Electronegativity also decreases from top to bottom in a group and increases from left to right in a period. Obviously, we know that metallic nature increases from top to bottom in a group and decreases from left to right in a period, right? Did you understand? These are the basic things of periodic table. Okay, let us discuss few definitions such as diagonal relationship, Lanthanide contraction, anomalous behavior kind of thing. Okay, let's see now. A Lanthanide contraction means This is mostly, it happens in 4f orbitals because they are lanthanides, right, in which when an electron enters into the sublevel of a 4f orbital, especially in 4f orbital, then what is the shape of 4f orbital? It will be somewhat different from a normal shapes, right. Because of its peculiar unidentified shape, the shielding and the screening effect of this particular orbital is very less, because of which the nuclear charge increases suddenly and therefore an atom or its ion size decreases. That is why it is called as lanthanide contraction. Especially in lanthanide atoms or in the lanthanide elements, this 4f orbitals, when an electron enters into its sublevel of a 4f orbital, then the screening or shielding effect of this particular atom is very less because of its undefined shape or some kind of peculiar shape, because of which the nuclear charge suddenly increases and the atom or ion size reduces, right. There is an interlinked thing. What happens if this lanthanide contraction happens? That is, its melting point, boiling point and hardness will increase, which is also an application, right. And this happens most of the time in +3 ions, right. In 4f orbital itself, that means in lanthanide itself, only few elements with a +3 have more influence of this lanthanide contraction. And there is also a chance of inert pair effect, right. What is inert pair effect? That is, we know that in inert gases are completely filled. Since they are completely filled, there is no need of reaction, right, which means there is no need of an external electron to be donated or to be accepted, isn't it? Because of which they are highly stable and inert towards most of the reaction, right. Because of which, because of this lanthanide contraction, most of the lanthanides face the condition of inert pair effect. Okay, did you understand? Fine. And there are a few more things to understand, such as anomalous behavior, in which we discussed in Mendeleev, right, which means different combinations are kept in a particular table which does not have similar properties, right, kind of thing. You can refer to the previous sessions. And one more thing is diagonal relationship, right. If we observe in the periodic table itself, there are few elements in which, if it is lithium, lithium is second group and second period and the first group, right, whereas beryllium is second period and the second group. Then here if I observe, lithium will have similar properties of magnesium, beryllium will have similar properties of aluminum, boron will have similar properties of silicon, right. This kind of diagonal relationship is maintained through particular groups and periods. This will be valid only for 1, 2, 3 up to 4 groups, but not more than that. Clear? This is what a diagonal relationship is. And if I want to compare between the similarity between in a same group or in the same period, in the same period or in the same group, is very much better when compared to this kind of diagonal similarity, right. Then why do we discuss is, we have to discuss everything in different ways, right. Fine. These are the basic things of periodic table. Fine. If I want to conclude everything, what did we discuss from the starting? We have started with the basic need of classification. Then we discuss about the different periodic tables, starting from Dobereiner, Newland law of traits, then Mendeleev's periodic table, then Moseley's periodic table. We also discussed about this Moseley's long form of periodic table. We discussed its specific features and its disadvantages, advantages, right. Based on that particular table, we discussed about the variation of periodic properties of a particular elements. That is, we discussed few properties such as atomic size, ionization energy, electron affinity, metallic nature, right, electropositivity, electronegativity, right, isn't it? Fine. And after that we discussed about few other properties which are not being specified in our previous topics, right. Did you understand? Fine. This is the basic introduction and broad explanation of a periodic table. You can read about this further in other higher classes Okay, fine. This is the end of the chapter. Let us meet in the next session with a new chapter of first year chemistry. Okay, thank you.